Can you hear me? Hello? Can you hear me?
Yes, sir.
Yes, sir.
I've got into trouble like that. Okay, now I will start. Let's see that. Shouldn't. Okay, let me start that. Basically, note 20 that basically, oh, sorry. Note 19 that basically I want to talk about Heinbodel theorem. Okay, first of all, you should understand Heinbodel theorem. Statement is very simple. Let me tell you that if you have XD metric space and phases, of course, you can assume non-empty subset of X, then if A is compact, then is closed and bounded. But the converse in Yan, the converse did not be true. Example is that if you take xt, you take xt, t discrete metric, and x infinite. And we have seen in this case only compact subsets are finite, but x itself, because D itself a bounded metric, so x is closed. In this case, x is closed and bounded. But not compact, because I have chosen x infinite, but not compact. This is the simplest counterexample. So actually, so what the importance of Heinbodel theorem, that if you have taken Rn, Cn is just isometric to onto to R2n. So it follows immediately as corollary. So if you take this, then Heinbodel theorem, HP theorem says a non-empty subset okay, that is theorem 5.12. Taken that A of Rn, you have taken Rp, it doesn't matter. Rn is compact. Here nothing is else this, so I am writing also again, is compact in if and only if is closed and bounded. Here Webster made a comment that If it is compact this way, it will happen for every metric space. So strength of the Hein-Bodel theorem actually is in this direction. That means a subset if it is closed and bounded in Rn, if that means this direction. Sorry. If A is closed and bounded, then this. So this is the Hein-Bodel theorem. Okay. Hein-Bodel theorem I have already I told you about the applications on that, particularly that problem. Part of the problem I have given in minor. Okay. So that, and here I have given historical reference. Heinrich Heine was a German mathematician. He worked on PDE and special functions. Heine introduced the concept of uniform continuity. And Emil Borel, that I told you, was one of the founders of the modern theory of function theory, along with Bayer and Lebesgue. In fact, Meyer theory, particularly Borel, Lebesgue, and Bayer, they come. That I said. And Hein-Bodel theorem, we are calling at that Hein and Bodel. But actually, it should be called Hein's theorem because in the bottom of page 168 I mentioned it was in 1872. Heine gave proof of this, while Borel published his proof much later in 1895, 23 years later. Okay, so it required scholarship to discover the difference in contribution to this result between Heine and Bodel. Okay, so that is part of history of mathematics. Why two name scheme? Particularly, it is so different, so many years, 23 years. So actually, it should be called Hein's theorem. Okay, so I want to give an easy proof of that in a sense. Okay, right. So what is the easy proof? Remember that last time I did a result that if you have a topological space, if you have a compact set, and if C is a closed subset, C is closed, then it implies C is compact. How we prove that Hein-Bodel theorem. So this is first the outline I'm explaining that. Okay, right? So that this is compact. Closed subset of a compact set is compact. That I have proved before. Now look, here the idea is if you have closed and bounded in Rn, you can think R square for your convenience. R square means is this slate, this paper. Closed and bounded. Okay, suppose you have in Rn, A is closed and bounded. Here I took K actually. Okay, so you can take K. I have reason for K because when we have the sequence and that everything we consider Xn and that closed and bounded in Rk, then you see that we can have that A will be contained in something like this. There will exist that. Basically, this is signal called parallelepiped in 3 dimensions. Okay. Basically, if you have this, every coordinate points in the coordinate you have this. I told you that it will be bounded in R square. Then when I was doing that problem, that it will be bounded if and only if you separately talk about the coordinates will have to be bounded. So that I will get a interval A1, B1, closed interval, such that x1 will lie in between this here. Similarly for xk. So A will be bounded. Forget about closed first of all. Bounded. A will be bounded if and only A is contained in a set like this. This is we are calling cell, K cell particularly, because we are doing in R case we call it K cell. But actually in three-dimensional name people call it parallelepiped. It looks like a cell actually. Okay. So that it is called K cell. So A is bounded if and only if you have this. Now the thing is, this is closed. This is easy to prove that. Okay, because you can do it by sequence also. Okay, then look here, a sequence will converge if and only if the coordinate wise convergence, and coordinate wise convergence in this is closed, so that limit has to be here. So it will be that. So it is easy to prove that this is closed. Okay, now if you can prove that, now look, that means where A is closed to it. So this will actually close here, this case cell, closed and bounded. Actually, for Hein-Model theorem, I'll prove this is compact. This cell, K cell, this is compact. Once I can prove it, now look the idea. The Y closed where you will be using. Since A is bounded, it is contained in this. Okay, and this I'll prove. This a K cell is compact. So that it will be a, now if A is closed, so A will be the closed A will be a subset of a compact set. I will use this result. So A will be compact. So ultimately it boils down to prove this. The K cell is compact. Okay, that I called F here. Okay, definition 5.3. Okay, so that now 5.3 diameter, you look here, when you have in this paper, it's cell, that is the rectangle. Look here, diameter will be the actually length of the diagonal. This is the largest thing. You have this. Similarly, but two diagonals are the same length. This will be this. But this you look, this is if you take A, B, C, D, then Pythagoras, P square equal to CD square plus PT square. Look, this is to go a difference between the x coordinates. Okay, suppose if you have x1, y1, x2, y2. So CD BD square will be actually this will be x2, y1 actually. Okay, so this will be x1 minus x2 square. On the other hand, CD, look, this is y1. This is if you take x3. This is y2. So this will be actually x4 y1. This will be how much? This is y. This will be actually x1. This will be y4. Let me see. I'm not very sure that whether I'm writing it correct at that. x1 y1, x2 y1, fine. This will be x2 actually. x2 y2, and this will be, no, this will be this one. Wait a minute. This is y1. I have taken y2. So this is also y2. Okay. So that this difference will be y1 minus y2 square. So you'll have to take the square root of that. Okay. So that exactly I am doing in that. So in YAL for K cell, the diameter of that F, usual diameter definition you have given. The soup of that. This is the metric, usual metric in F in RK. Delta is that. That is the. So this is this. Okay, right? And now look, if you have this, wait a minute. Now, suppose you have this, and now you take the midpoint here. I'm doing it for k equal to 2 to understand better. And here you take the midpoint. If you join them, for similar triangles, rectangles will come. Okay, like R1, R2, R3, R4. Okay, now look, here his diameter will be, look, ये यहाँ पे डी diameter पहले ये diameter था. You can easily prove that this diameter will be half of this. Okay, right? This diameter will be half of this diameter. Now again, if you do it here, midpoint, if you add, this diameter will be half of this. That means if I keep doing it, if you join midpoints and then take the diameter, each time the diameter will be half of that previous one. Okay, right? Now, why I'm doing it? Because I want to prove this is compact. Okay, so that look idea that if you start, I'll have to take any open cover. Take any open cover. Has a finite subcover. That I'll have to show of this cell of K cell. Here it is actually 2 cell I am doing it. Has a finite subcover. Argument is very simple. Now suppose I have a cover of this which doesn't have a finite subcover, which doesn't have, suppose, contradiction. Now look, when I do this for subrectangles I get, and at least one of them won't be covered by a finite members of this, because if each of them is covered by a finite family of this subfamily, then the whole thing will be covered, because only 4 you have, will be covered by finite subfamily. So this way, if I assume this, that is this 2 cell is not covered by this, the finite subfamily, that exactly argument I am doing. This I called, this is a standard thing. The finite subfamily doesn't cover. Then the next stage also, I will get one rectangle such that it will be covered by finite subfamily. This process I can repeat. So the process you repeat, now look. So this way, what will happen? Look, these are closed sets. That means geometrically the proof is very simple. That means you will be getting a sequence of closed sets. Look, what you will be getting, that I'm saying, F1, okay, let F be the curl, and if possible assume that F is not compact, then there exists an open cover such that no finite subfamily covers F. Let delta denote the diameter of F. As noted earlier, F is the union of 2 to the power k cells, each having diameter delta by 2, that I told you. Next stage, if you go divide by adding the midpoints, the next to the diameter will be delta by 2. So at least one of these k cells, that means you call it F1, you call it F1, won't be covered by finitely many. Now again, what you did between F on F, what you did on F, then you do the same thing on Fn, F1. So again, look, here you will get F2, which won't be covered by a finite subfamily of this. This way you will get this. Again, another thing, F3, that explains. Okay, right. Now look, R, K, This is complete. So I can apply Cantor's intersection theorem. And these are closed. And diameter at Fn, diameter of Fn is this. Whatever, if you take diameter, dFn actually, there I am calling delta. Okay, I don't know what notation I've used. Let me see them. Okay, Fn has diameter, I didn't use it. Now look, here page 170. This, I said one condition, diameter of Fn, call it T. Diameter of Fn is delta by 2n. Okay, right? And this is condition 2. And condition 3, that Fn cannot be covered by finitely many sets from U. Okay, that I will use later on. Now, this, by using Cantor's intersection theorem, this is complete. Everything I am working inside this. So this will be non-empty. Okay, this will be non-empty. Okay, right? Got it? Okay. Make sure that everything is coming from F. So X, so there is X naught belongs to this. That means X naught belongs to each of them. Particularly X naught belongs to F, because each of them is a subset of this. So that I get this thing. X naught belongs to intersection Fn. Okay, right? Same thing. And that is particularly X naught belongs to F. To F. And don't forget, this was the cover. Sorry. U belongs to U. Okay, because this was a cover. I started with the cover. I assumed it possible no finite subcover covers F. So, but then since it is here, so it is here. So there exists U naught belongs to U such that X naught belongs to this. Okay, right. But in metric, this is open. So there exists R greater than 0 such that, okay, X naught belongs to Bx naught R U naught. This I get because U naught is open. So X naught is an interior point. Okay, right? Now you see that where we are getting contradiction. Now if you take delta, I can choose n such that I have this. Okay, delta by 2 to the power n. Suppose you have this. That I can always choose large n such that it happens. Now look, what will be? I'm saying then Fn must have this. This is very simple to do it. Take any y. Okay, this is X naught. Okay, now look, you need to show that Fn belongs to this. Fine. Now look, that Fn, if take y belongs to Fn, now T y X naught. Okay, take any y. Okay, now how to do that? G y X naught, you'll have to show this is less than R. Okay, right? Got it? How to show that? One can easily see that Fn is contained in Bx naught R. So y belongs to Fn, and I'll have to show this is. How do you do that? Okay.
Diameter delta upon 2 is 10.
But I only know, but that is the question, that x naught. Look, here you need to use the fact x naught also belongs to Fn. X naught belongs to each intersection. So x naught belongs to Fn for all n. That's the thing you need in characteristic intersection theorem. Whatever n you choose, x naught belongs to this. But dy, that means x naught belongs to Fn, y belongs to Fn, and diameter of Fn is this. So that you are getting this. You need to know that and note that x naught belongs here, each Fn, and this is less than this. Okay, so that y belongs here. Okay, you got it. Now Vx naught are contained in U naught. That means what? Fn is being covered by U naught, one single element, but U naught was a member of this. But how I got Fn? No, Fn is covered by a finite subfamily of the covered U, the script U. No Fn is covered. That's the way I have chosen. No Fn is covered by a finite subfamily of this. But here I see that only one. Here only one is covering this. So I am getting a contradiction. So that why this happened? Because in the beginning I assumed that it doesn't have any finite subcode. It must have a finite subcode. So that KCL will be compact. Okay. And rest I have already explained that. The proof that. Okay. I said that I was taking the KCL. Actually, when you have A closed and bounded, now closed and bounded in RK, I'm saying in general you can take that. Since A is bounded, you can take the K times. Since A is bounded, look, A is bounded, I can see that. If and only if there exists M greater than 0 such that xi less than equal to M for all I 1 to K. And xi, x1, x2, this thing. That is which coordinate is this? That's what I can put inside the nice things. Okay, and that is compact. That's what I proved. But this is obviously closed. That you can use Bolzano-Weierstrass theorem. Okay, to prove that. Okay. In next semester, I will do topology. Then the product of closed sets will be always closed sets. So this is closed, and now we are using this is closed subset of a compact set. So it is compact. Okay, this is the proof. Okay, that I said that. Now the proof of theorem 5.12. Okay, now I put a remark that sequential characterizations using that, but I told you. But here I would like to mention. Suppose you are using sequential characterizations. So R square you take. This by using sequential characterization. Remember the last time I did that a subset in a metric space is compact if and only if every sequence in A has a subsequence converging to a point in A, because A has to be closed, converging to a point in A. Now look, if you use this thing, how to prove that? That's the way the book, the Alipranthes Berkinshaw, they have used, but be careful, you should look at the proof. Look here, if I take a sequence, here the sequence should look like this. So that take a subset of R square, of course not empty, and take a sequence. It will come like this, right? Okay, right. Okay. Now, A itself is closed and bounded. So if you take a sequence, it will be a bounded sequence. It's a bounded sequence. Okay. Bounded sequence means both coordinates are bounded. But that means xn is a bounded sequence in R. Okay. Since A is closed, automatically it will be there. It won't be a problem. Only I'll have to show the convergence subsequence. Now, if you use Bolzano-Weierstrass theorem, it will have a subsequence. There exists a subsequence converging to a point X. Okay, right? Similarly, we will do that for Y. That Yn is a bounded sequence in R. So there exists a subsequence converging to a point in Y. That means Xnk, Ynk converges to X2. So this is coming from A, because these are the chosen from here, A. So you are getting a subsequence. You are getting subsequence converging to a point. Since it is closed, it has to be there. This is usually the students prove it. This proof is wrong. Can you tell me why it is wrong? This proof is wrong. This proof is wrong. When Alipranthes Berkinshaw, if you look at the book, you will see that. What will be this? Do you have any idea why this proof is wrong? In measure theory, also you need this kind of technique in that. Okay, that's why I made a comment of like this. Well, you can't tell me why the proof is wrong. Let me tell you the proof is wrong. Why proof is wrong? For xn, yn. Look, I am having a subsequence. Actually, I should have written kn. Did I write? I should have written kn actually. The function. It doesn't. But it should. Look what xkn means actually. It means you had a sequence from this. Here, this is R square. I've taken. Okay. This. And then you got subsequence. That means here you got, remember that, the phi. Okay. So that we are calling kn. It's coming. K going to kn. And then xkn. So this is actually, the subsequence means what? Actually, this is f dot phi. Look, subsequence, this function is involved, though it's a notation. But on the other hand, when you take yn, ykn, you can't use this. This is a function. I may have a different function here. It's strictly increasing function. So for yn, I will have this function like something like this. Psi. Here it is. If it is coming, it is in R actually. Okay. Okay. So that. So here subsequence will be this. this function and this function need not be same. So this is the problem. Just because I am using the same notation, I am not actually allowed to use the same notation, because a kn actually indicates this function. Okay, and this function here can be different. Okay, so that's why the proof is wrong. I was doing x kn, y kn, I was telling then this. If you have this, then it's not a problem. Only thing is that this kn you cannot choose. Then what will you do? That's the question. That is the simple trick. Look, I can't do it. Here I don't have, I told you, I explained that. Functions are different. This thing. So actually you are not allowed to use the same notation. But how to overcome this? Now look, what I will do. If you have xn, yn, this sequence, fine, where you are getting xn to xkn. Look, here I will start with corresponding index that I can take ykn, but I am not saying that ykn. Okay, that will be a subsequence, but not necessarily the same subsequence I will get by the compactness and that. But I am saying, given xkn, choose this subsequence ykn. Okay, ykn. Now on this you use the compactness. Look, yn is a bounded sequence, so ykn, any subsequence is bounded, so it will have a convergent subsequence. Y, K, N, G. Okay, K, N, G. Like this. Okay, it doesn't matter. I have written NKG, that I explained to that how people write Kn or NKM, NQ. Okay, now you do that by the compactness of that. Now look, since xkn converges to x, so any subsequence will also converge. So it will have this subsequence. Now I consider this subsequence. This it takes. That's not a problem. So this will converge to x. And this converges to y. So x, k, n, j, y, k, n, j converges to x. That finally got. So you need to ensure that this is the trick. You'll have to start with this. Make sure Aliprantis-Barkinshire, I said theorem 7.4. You can read that. Page 51. Look, here I have done it for 2. Then, in fact, if I have an R cube, then again I'll have to this. I'll have to start with this subsequence here, y, k, and j. And then x, y, z, to z, k, and j. And then I'll have to take this subsequence. That's the way I'll have to continue. Make sure you read this and try to understand the intricacy in the proof. And because that will give you the precise idea, understanding of subsequence. In measure theory, we use this technique, but you'll have to be careful. The way I was writing first, if you write, if you write this, not only I will give you 0, other teachers also will give you 0. Okay, particularly in the measure theory students. So that make sure that is the thing, the remark I tried to hammer out basically. I said, read the technique of the proof of this result given in the top of the page 52 of Aliprantis-Barkinshire very carefully. Okay. Now, I said that. Okay. So that this is the proof of Hein-Model theorem I have given you. Look here, sequential characterization using, if we understand the trick here, it looks simple, but the point is that you are using sequential characterization and compactness in a metric space, which was not easy to prove. Okay, now look here, that theorem 5.1, let X be a matrix, so A be a non-empty compact set, then every open cover has a Lebesgue number. Okay. Here, look, but I'm saying that previously I proved that. Remember the previous result that here I say I gave a direct proof of that. Here, what I did in a previous result, that if every sequence has a convergent subsequence A, suppose if you take a metric space xt, let me tell you that what is this thing? That page in my note I am trying it. Page 113. Look, if I say it that A, I proved that here hypothesis I assumed that every sequence xn in A has a subsequence again converging to a point in A, and then conclusion I got every open cover of A has a Lebesgue number. Now look, basically this is equivalent to, now you know bisequential character, A is compact. That means if A is compact, every open cover of A has a Lebesgue number. That's the proof. That's the result. Okay. That exactly theorem 5.5, 15. 5.15 then. A be a non-empty compact substrate, then every open cover of A has a Lebesgue number. So if you use this result and use sequential characterization of compactness, then it is immediate. Okay. I said here I have given a direct proof. I have the reason to give a direct proof of that. Okay. I have a reason to give a direct proof. But okay, it's better because often you may be asked questions in some competitive exams also on that. Because if you take that proof sequential characterization, then people may ask you that how do you prove that? Then you will be in a big soup. So, but rather here, if you look at that, okay, so that it's the direct proof just by using the compactness. Okay, so that here, look, here the result is that this xt is a metric space. This is hypothesis. Compact. Then every conclusion, every pin cover of A has a Lebesgue number. Okay. Now look, I'm just using the definition of compactness. So take any open cover. I'm not using sequential characterization of the compactness in a metric space. I'm just using the definition of compactness. So let any open cover Qi open cover of A in xt. Okay. Right? Now Look, use the definition of the Lebesgue. So you take a point x belongs to A. Pick up any point x belongs to A. Now Uy is an open cover, so x belongs to some Uy. Okay. Look, each and each Ui is open in this. There exists epsilon x greater than 0 such that I have this. I have taken 2 epsilon just for computational purpose. Is Ux. First of all, x belongs to A you are taking. So x belongs to some Ux. So Ux belongs to this in this cover. Okay. Understand? Ux is a member of this. Since Ux is open, so there exists a ball. Okay. That means that ball radius I am calling 2 epsilon x. Okay. Right? That I did. For some Ux belongs to this, where x belongs to Ux. Okay. Now, so that if you now look that for each x you are doing on A. I have chosen x arbitrarily. And then I have used the definition open cover of that. So x belongs to some member here. That I am calling Ux. But since Ux is open, I will get an open ball. The radius will depend also on x. So that I am calling 2 epsilon x. So now look, this is the reason. If you take epsilon x, then I will have to take epsilon x by 2. Now this one I am doing for each x. So is an and each it is an open set, open ball. Is an open cover of A. But A is given to be compact. So it has a finite subcover. Okay, so there exists, look, A itself I am using as a index set. So that there exists x1, x2, xn, xk rather, xk in A such that I say note that A is also I'm using as an index set such that A is contained in union Bxi epsilon xi. Okay, I want to keep. Why 2 epsilon x cube? Because you will later on see I will be using triangle inequality. That's why I have done like that. Okay. Now choose epsilon equal to minimum of this thing. Now we can prove that by using triangle inequality. That I am not telling you, it is written here. That Bx epsilon is contained in some. Look, so there exists I. So Bxi to epsilon xi for some I, where I is lying in between this. For some. But this is by the way I have chosen. This is U. Got it? So that by definition of the Lebesgue cover, it is satisfied. Okay, hence epsilon minimum. Look, this is a Lebesgue number of that cover A. Okay, and that if you read these two lines, you see that y from 2 epsilon xi. When I went for a cover, I took this because of the triangle inequality. What I am using here. Okay. Now, here see that again I am telling you that I said when I took this, I said note here. Okay, I have made a comment that I am coming in page 174. I made a comment again, but I am right now I am telling you. Look exactly where he used compactness. Said every open cover has a finite subcover, fine, but actually used compactness here. That I told you before in one other proof. Because if I didn't have compactness, I could choose epsilon equal to infimum of this. Okay, all these things. Infimum of this epsilon x. Okay, x belongs to A. But the only problem is that this could be 0. This could be 0. Then the whole proof won't work. Look, in the radius, it has to be always positive, strictly positive. So that is the problem it is happening. But when I am taking finite the look, then actually minimum is one of them. So epsilon is greater than 0. This is the thing, it will ensure. So that, and I previously commented that compactness is a generalization of finiteness. This is one justification here. Okay, because of compactness, I have reduced to a finite thing. So it's a generalization. Okay, now okay, let me finish this thing. I think we can finish it. Okay, I'm just coming back on that. I will talk about the problems also on that. I'm just coming back. Hello? Hello, are you ready?
Yes, sir.
Okay, here you see theorem 5.6 important that I proved before. What is that theorem 5.6? But I said to direct proof that. I said if you have a function continuous function and this is compact, then this is all hypothesis implies f is uniformly continuous. Okay. Look here, previously I proved one result, earlier result. But I'm trying to say that direct proof. Earlier result, you have continuous function at every open cover of X has a Lebesgue number. And then f is uniformly continuous. This I have proved before. Okay. So right now in the previous result I proved that if X itself is compact, then every open cover will have a Lebesgue number. So f will be uniformly continuous. So that this will imply from this result and theorem 5.15. Okay. But the thing is that it's better to have a direct proof. Direct proof is easier, much easier, because here you are using another result. Every open cover has a Lebesgue number on that. Okay. But if you go for a direct proof, you don't need to have this thing. And direct proof is simpler also. That and often it is asked in some exams and that. So that's why I've said that. But it is better to have a direct proof of theorem 5.16 without going to Lebesgue number. For the exams, including the competitive ones, such as UGC-NET, use the following proof and that. Okay. So that again, this I think now you should read yourself for that. Here two things is there. Again, you look, I am doing RXI I have taken, but there of course a similar technique that what you did here, that earlier theorem 5.15. So here you look that since f is continuous Rx greater than 0, here dx x prime, I am taking, I'm just explaining alternative proof of that. dx x prime less than 2Rx implies this x prime belongs to x implies I'm using the definition of continuity. Less than epsilon by 2. But when I am going for the cover that I told you, I am taking the cover this like before. Not this. So this is again I made a comment that is for computational purpose, for computation purpose that I did. After that, and now again I am choosing this delta because using compactness I will get finitely many things Rx1, Rxk like this, Rxn, and then delta I am taking minimum of this. And again this delta is greater than 0 because this is minimum of finitely many things. Actually we use the compactness here. Okay, so this is the thing, as I said, note here, and also I said 2Rx. So we should read this proof and it can compare with the previous one, the proof of the previous one. You'll see the basic technique is same. Basic technique is same. Okay, and rest is triangle inequality. I think you should read the proof yourself. Read the proof of this. I'm just telling you. What I have given here, direct proof. First, you do that. Okay. Second, compare it to the proof of theorem 5. When I say compare it, basically compare the technique. Compare the techniques. Of course, when I'm saying compare it to the proof, of course, means the technique of the proof. Compare the techniques of the proofs. Okay. So this you should do. I put a star mark on that. Okay. And remark already explained that all these things where you are using compactness. If you do not have compactness, everything will work. Only thing then you will have to take in phi inferior. But that may not be, that will be only greater than equal to 0. So if it is 0, then it won't work. But you may say sometimes it may come greater than 0. Of course it may come. But then you will have something other result than that. Under which condition it will be. Not necessarily it has to be compact. It is possible. Okay, so you should do that. Okay, I want to talk about the problems of that. Bhavna and Dhiraj will do it definitely. Okay, right? So that okay, first question to page 175. So you should this week I'm telling you, you should work with compactness seriously with Bhavna and Dhiraj. Problem 1 already I have done it. I told you that what is the idea of the problem. The minor one I have given part of this. Okay. And problem 7 page 55. ये क्या है देखना पड़ेगा. Problem 7 page 55. In compactness, you should do as many as problems possible. Otherwise, you won't understand compactness. Okay. Well, actually, I'm not going to do the problem. You should do it. If you can't do it, you can ask Bhavna and Dhiraj. What is it? Here you have this thing, a function. Range and domain, they are same. Okay. Just he's saying this. Okay. And he is giving this. First of all, here, if you have, when you have a function from x to x, then if you have this fx equal to this, if you have, you don't need to have it. Okay. You don't need to have it. Okay. Then if you have it, then x is called a fixed point of, that is an area in mathematics, that is the fixed point theory. So x is called a fixed point of f. Okay. Right. Here he is saying, suppose you have this t fx prime less than dx x prime for all x prime belongs to x. Suppose you have a function. Such function is not unusual, it happens. Okay, right. Let me see that. Of course, you'll have to do x not equal to x prime, because if you have x equal to x prime, then this will be same. So it will be 0, this will be 0. It won't be strictly. Here I am saying strictly less than. Understand? So that's why you'll have to write this x not equal to x prime. Okay. So this is called a contraction. Okay. And they think if you have a contraction, if you have a map such that you can prove, that is not required, you can prove that such a map will have to be continuous. Okay, every contraction is continuous. Okay. In fact, if you have this is less than delta, delta equal to epsilon, you can choose. It will be continuous. So if the problem says if it has a contraction, it has got a fixed point. Okay. Right. It has got a fixed point. But look here. Wait a minute. What here is saying, this is compact. There is a problem number 8 that is not related to compactness, but talks about contraction. That is called known as Banach's contraction problem. That problem number 8 in this page, page 55. This is not related to compactness. It is related to completeness. This is called Banach's contraction principle. And this is, I don't know whether your teacher is using. He use in ODE also, the existence of a solutions. You need that there. Banach's contraction principle. Okay. So this is compact, that you'll have to prove it has a fixed point. Now look, I am just giving an example of nice example of a fixed point, but that is not related to compactness. That is related to something connectedness that I will teach later. But I think in BS you did what can happen. Suppose you have this. Suppose you are doing from 0 to 1, and here also 0 to 1. So that you are having a square. Call this one. Okay. And this is your diagonal. That is y equal to x. Now, if you take any continuous function, of course, with the usual distance, here everything usual distance to this. Now, if you have continuous function, you will have a graph. Now, look, this will be like this, something this. Okay, right? Why I'm writing this? Continuous function means you must have continuous graph. Now, look, I am saying this. Now look, I'm saying such a function must have a fixed point. That means there exists x belongs to 0, 1 such that fx equal to x. Y equal to x. Look, this is a fixed point. This is also a fixed point. F0 equal to 0. Here is whatever x is there, fx equal to x. Here is one fixed point. Here is one fixed point. Okay, here is one fixed point. I have drawn this one. But suppose, can you have such a function which doesn't have a fixed point? Look, is it possible? That f does not have a fixed point. I have given you this thing. This, like fx equal to, you can take x square. Even though identity function, of course, is there, that will have a fixed point. Fx equal to x square, you see that 1 is a fixed point, 0 is a fixed point. Okay. So such a function is there. I'm saying, is it possible to look, if it doesn't have a fixed point, then you see what will happen. That means it should not cross, it can't cross this. It can't cross this. Okay, right? Then what will happen? That means either the graph will be above this line or below this line. If it is above this line, now see, even if I start this, that means one can't be in the domain of that. I won't be able to cover 1. I won't be able to cover 1 because the moment I cover 1, I am getting f1 equal to 1. On the other hand, if I go here below, I won't be able to cover 0. Okay, so that no, to think about it, it must have a fixed point. Okay, fixed point means in the metric space you can also take a graph the thing. This is x coordinate. This is here same x coordinate, xt. Basically y coordinate, but y equal to x here, and that is and this is this diagonal y equal to x. So it will must cross to have a fixed point. So this is a particular example when x equal to this. Okay, right? So think about it. So fixed point itself is an area in mathematics and that. Okay, it has a lot of applications also that, particularly applications applied mathematics and that. Now the question 3, number 11. Problem number 11, page 15. Oh. Well, 11. Now look. Yes, page 55 of the question number 3. This is optional. I am taking optional. Okay, but let me explain the motivation behind this problem. Suppose you have this. If you have this, suppose this is an isometry. That means f t fx prime equal to dxx prime. For this question I have given before that I just mentioned, not given. For all x prime, here x prime may be equal to x, then it will be 0 on the book, belongs to x. That means f is an isometry. Okay, here I am saying if xt is compact, then f has to be onto. Look, an isometry need not be onto. Isometry by definition will imply f is 1 to 1. Like from r to r square. Look, if I give this usual distance, x, you take x0. This is an isometry, but it is not onto. Okay, but he's saying if x is compact, then f has to be onto. Look here, r is not compact. Okay, f is not onto. In fact, simpler example you can see that I am giving you. Another example you can look. If I take this n to n, usual distance, but I am taking n to n plus 1. This is not onto because 1 doesn't have the preimage, not onto. But it's an isometry because this is not compact. This is not compact. So that is the importance of the problem. Okay. I'm just saying it's optional, but if you want to try it, you can use, don't use the definition. You can use sequential characterization of compactness here or accumulation point. Every infinite subset of X has an accumulation point. Actually, if you assume this is not onto, you can get a contradiction to any one of the conditions you assume that the use that every infinite subset of X has an accumulation point or every sequence in X has a convergent subsequence. Idea I'm telling you, just again I'm telling you, it's optional. But look, if you have this X to X, F, again you can take F because range is same. That means in general you can have the map F to the power n, when you compose n times. Look, F is not onto means Fx is a subset of proper subset of X. Then what will happen with Fx n between F, sorry, not Fx n, sorry, Fnx and Fn plus, look, this is this, but will it be equal? If it is equal, then you can prove F will be onto. If it is not equal, then you will get a contradiction. Okay, right? Well, so you think about it. If you can't do it, it's fine, but there is no problem in thinking. Okay. Look, when you think about a problem, it is not your ultimate goal should be to have the solution, complete solution. Even if you keep thinking about the problem, you will discover many things. Your ideas will be clear, concepts will be clear. In fact, Hurston's algebra book, in B.sc, you have, I think some of you have looked at. There he has written, it is not always required that you must solve the problem. Even if you get partial solution or if you get thinking, get something out of thinking on the problem, still it's good enough. Okay, so think about it. Now the question 4, this is very important, particularly when you do function analysis. That's like, suppose I have the graph. I have talked about graph you always use. Look, when I have a function from R to R, graph of this of F is actually what? X Fx. Which is a subset of R square. The graph of F is not a subset of R, it is a subset of R square. Okay, right? So that R square also has topology, usual topology. I can talk about, think about whether the graph is closed or not. Okay, now you can see that if you have a continuous function, now look what will be, that means if I have this function between two metric spaces, that means graph of F will be a subset of X cross Y, X Fx. Look, this is a subset of X cross Y. Look, some students they get confused. Graph of F, sometimes you write also GF. It is not equal to X cross Fx. Look, X cross Fx, if you use the definition of the Cartesian product, it means x1 Fx2. This, where x1, x2 belongs to x. Look, these two need not be same. If you write, because X cross Fx by definition is this, you are having an element from X, you have an element from Fx, so they need not be same. Whereas graph, this has to be same. Okay, so graph is not this. You should understand the graph. Now look, in R to R function, I went to R square graph here. Graph of F. But there already I had a metric. But how that metric came? Look, on R square, you'll say the metric came like this. R square, the metric was this. Took metric x1, y1, x2, y2, the usual distance metric that I am calling D. Okay, but that was actually x1 minus x2 square plus y1 minus y2 square. Okay, but this metric also I could give. If I give it, look what is x cross y, then what will come here? X1 minus x2. This is actually, so I will have this metric. If I do it, I will have t x1 x2 square plus to take xt y rho. This is rho y1, sorry, rho y1 y2 square. Look, this makes sense because these are all real numbers. Okay, I can give this a metric between the distance of b. If you take big D, okay, D. It will be a metric like this. The way you prove here, same proof here. It's a metric. But often, this is called a product metric. The product space you are doing, it's called a product metric. But the problem is that in R square, you have also seen that if metric throw up, it is difficult to handle because first of all, in the inside you have square, then you have square root. Okay, so that actually that is the idea of the equivalent metric. Equivalent metric, if I have simpler equivalent metric, I can deal through equivalent metric. Now look, R square, I could give two more equivalent metric. So what is the two equivalent metric in them? I could give, look here, I have this, I could simply give this another metric. Suppose you call it D1 or D2. I am giving this thing. This I could give, and you can show these two are equivalent. Not only that, I could give another metric. It all depends on your choice that which one you will feel comfortable in computing. X2, Y2, I am giving this max. This will be also metric, and that will be equivalent to all these two metrics. Okay, right? So actually, these two are easier to handle than this. Even then, max, it is this one, second one is more comfortable than this one, easy to handle. Okay, right? Got it? Here I say that you should look at that. What is the product metric you are taking? So that in question 4, when I am going for the product metric, that I said product metric. Usually for product metric, we take this one. So that if you have two metric spaces, and on this, if you take this, sometimes you use the D cross row, that means the product metric. It immediately tells you from out of which two metrics you are getting the product metric. So that T cross row, look, how will I get it? This will be x1, y1, x2, y2. Look here, what will I have? This was actually in R square I am doing, but actually it is d, the first one, dx1, x2. And this will be rho y1, y2. This usually we take the product matrix. So that now we can talk about the topology here, closed sets here. So that here I said important must do it. Problem number 14. I think it is page 56, I think. I wrote it is actually page 56, next page. Okay. I said you must do it. Okay. Then F is continuous if and only if G is the closed subset of this is a compact metric space. Now look, if you this thing, now I'm explaining the more background of this problem. So suppose you have this. Okay. And if it is continuous, if F is continuous, then graph GF, graph of F is closed in x cross y. So with respect to that metric. Okay. Here the closed you can use sequential characterization. It will be easy to prove. Okay. Just telling you why you must do it and what is the importance of that. I am trying to explain the importance of this. Okay. Right. So what is it? Look, now on the other hand, if you take this function, look, its graph is what? Look, its graph, GF. And this point. This is closed because if you take complement, because R square minus GF is open. And I told you that is equivalent metric in the R square that we usually take. So if you take product metric, it doesn't matter which metric is open in R square. So this is closed. This one is closed. But this function obviously is not continuous because it fails to be continuous at 0. Okay, so that this is not sufficient. If G graph is closed, then it may not be continuous. But you see that here, though it is closed, but it is not bounded. Graph is not bounded. Okay, right? So that here is the difference, I think. If that in the problem 4 is saying if y rho is not compact, then for a function, the graph may be closed, but f is not continuous. Here in Alipranthes said if this is compact, I have given the counter example. This is counter example. I talked about the counter example, but that I have given you. If this is compact, because R was not compact, then it will be if and only if. That means if you have a continuous, sorry, let me write it, not. Suppose you have a function, then f is continuous if and only if its graph is closed in that. Then the other direction. One direction is always valid, that if f is continuous, then graph has to be closed. Okay. But if the graph is closed, it may not be continuous. This is the example, one counter example. But if the range is compact, okay. Look, if range is compact, then I cannot have such a situation. Because in a metric space, any compact image will be the look. If your graph is closed, think about it. Then what will be the happen that this kind of situation I cannot have it. So I am leaving it to you. First do the problem. Okay, it won't be difficult. You can use sequential characterization. Okay, because look, you are doing in a metric space. When you want to say graph is closed, you want to show this xn goes to x implies fxn goes to fx. But here I am telling you one hint. You'll have to show this. Suppose this is not true, do it by contradiction. Then you will end up the situation the graph cannot be closed. Okay, do it contradiction. Do you use a sequential characterization of continuity and use contradiction. Okay, right? And so this is compactness is coming. These are all problems with the compactness and that. And question 5 already I told you that in R I did RK. Now you see that. Previously I did, if you have A plus B, it is defined. It is because in any linear space you can define it. If A is closed, B is closed, it need not be closed. If A is closed, B is closed, A plus B need not be closed. But if one of them is compact, then it will be closed. That means suppose this is closed, this is compact, will imply, it is getting late, A plus B is closed. But it may not be compact. But if both are compact, that is the problem number 5. Now I should tell you that here also you will be using sequential characterization of compactness, but be careful here. That technique, I was telling you the Heinz-Model theorem, the alternate proof, that same technique you need. Don't confuse that. If you take with the subsequence, you come here, xkn, then you start with a subsequence ykn, and that will give you yknj. So you will get xknj. So this thing you will do that. Okay, make sure question 5, I may choose one of them. Okay, right? In fact, when you are doing it, so the metric space RK particularly, I can consider complete subset. You use you prove that if both of them are complete, if A be complete subset, both are complete, I replace close by consist, may not imply A plus B is complete. Even in R, you can find such a counter example. Find an example in R. Okay. Look, R is complete, so any subset will be closed if and only if it is complete. So use that fact. I'm just mentioning that. Sometimes in interview, some questions instead of close, they may give that. You will wonder that how to do this. Okay. Right. So you should do that. Okay. That I said question C, and question 6. I think you understand the diameter. Diameter will be obtained. Basically, you need to use sequential characterizations. And question 7. Okay, right. I'm just mentioning the question 7. Question 6, you can see that diameter will be obtained. Questions L infinity R. I have given a subset. Actually, usually you do it in L2. There is something related to called Hilbert cube. You can see that. What is Hilbert cube? Sorry. Here I say that show that F is Inyal-Heinbudel theorem is not true. I said show that F is closed and bounded. Okay, it's not difficult. F is bounded obviously because you are getting by this. From 0 you take it will be actually inside in the closed unit ball. So it is bounded. And because of less than equal to I am taking, you can prove that this will be closed. You can use sequential characterization. Now I said, but F is not compact. So that Heinbudel theorem again I am saying it's not valid. It's a nice space. It's not like discrete space. Okay. I said even that even if you can't do this problem, at least try to understand this problem. Okay. So it's just up to you. Okay. I think it's all. Okay. Now tomorrow I will start note 20, that which is pointwise and uniform convergence. I will take class tomorrow and Friday. Saturday I won't take class. Then I will take class, I think November 8 after this. This is October. After this I will take class the last week. That will be November 8, I think. Okay. So this week only 2 more lectures I will take, 26 and 30. And this is not March. This I want to finish. Okay. And connectedness, 1 lecture that I will finish summary. Okay, I do not think I will need 3 lectures in them. Okay, so that tomorrow I will pointwise uniform convergence. Here I should tell you that there is something typed note exam. That is part of my book, published book. That I have given you the history behind pointwise convergence and uniform convergence. That note you should read it. It will give you a better understanding between the difference between pointwise and uniform. But first let me teach you tomorrow pointwise convergence, uniform convergence of sequence of functions, that is note 20. Then you should read that note 21. Okay, see you tomorrow around 12 noon. Okay, bye.